All right, so what we'll do is continue with our second conversation. I know it's 10 minutes overdue. I'll try to cut this short. I thought that the last conversation was going the right direction and quite interesting to hear what China Mobile had to say. So it's important to let that conversation go forward. The premise of this conversation is basically on 5G and 5G Fronthaul, and I'll skip through some slides just to be able to address the meat of this conversation very quickly. There are certain challenges in 5G, right? 5G deployment models call for functional splits that happen in the network, and new network topologies are required. For example, just beyond backhaul, mid-haul and front-haul will come into play. That was something Mr. Gao was just mentioning. And then the access to radios in certain topologies is going to be limited. There's going to be sparse fiber, and we talked about DWDM in the past just 5 minutes ago. And also the need for the front haul is going to be slightly different than the need for the backhaul and the mid-haul in 5G networks, right? The focus here is to focus solely on the front haul applications. We talked a bunch about the packet networks and how they integrate with the slicing in mid-haul and backhaul, but let's focus quickly on front haul. So let's look at some of the splits that are going on in the 5G network. And if you look at the functional splits for 5G, there are essentially two major splits that are being defined. One is where the mobile edge computing cloud meets with the DU, and then another split where the DU actually talks to the radio. So as we look, we can go into and dwell into why each split is required, but it's pretty much looking like the industry is coming to a head at a split 2 sort of thing for the CU, which is the central unit, and then a split sort of a 7.1, 7.2 sort of for the DU and the RU. And the reason for the splits is the CUs and DUs have different topology requirements. In certain cases, the 4G LTE network has to work on the same network, as well as CUs and DUs might be co-resident, DUs and RUs might be co-resident. There are many different applications that will come into play. But the major reason for the functional splits is the amount of bandwidth that is required from a network point of view that has to be transported to the radio. So if we go down the arrow, and we did what was done in 4G before, which is take CPRI directly to the radio, the amount of throughput that is required is going to be insane. It's going to be 230 to 240 gigabit per second per instance. That is non-manageable. You have to take this network and you have to make it manageable such that the throughput can be maintained to the remote units. And that's where we're seeing the market sort of evolve to what is called the split 7.2, which is about 20 gigabits per second towards the front haul radio network. So based on that premise, let's look at what 5G networks will do for us, right? So what does a 5G network look like? We just spoke about it at length before, but there is going to be a packet core, a mobile edge compute core that is going to be generating the traffic towards the 5G. That will then talk to what we call a centralized unit, a CU. That is a packet core. And then from the CU, you will have 2 separate instances. You will have a distributed unit and then a radio unit, or you will have conjoined distributed units and radio units together. You might even have CUs and DUs put together and just talk into radio units, so i.e. a front haul link just directly coming out of the CU. Topologies are going to be different. Topologies are going to be different based on where the network is deployed, how the network is deployed, who the service provider is, and what the needs of the network are at that point in time. So what do different technologies require, right? So we can quickly look at it. Backhaul, the ranges, the distances are quite significant. You have lots of latency required, but as you go closer and closer to the edge, as you go closer to the radios, the latency requirements on these networks become quite significant. And in Fronthaul, we're looking at, sub-millisecond type latencies, probably less than 100 microseconds. From a logical topology point of view, if you look at a network, you want to break it down from a logical topology perspective. What does it look like? So a centralized unit up there has a backhaul tail to it, which goes to the packet core, and it talks to distributed units. That distributed unit conversation is what we would refer as mid-haul. That mid-haul is actually a joint packet network. It's carrier Ethernet, some sort of packet core, utilizing SPN. It could utilize many other technologies that are out there. It could be purely packet, for example. But from the DU out to the radios, you can think of that ring as point-to-point connections from a DU to a radio. And that sort of is the green spigots hanging out from the DUs all the way to the radio antennas. And that in the previous diagram was implemented as a ring, because the ring is the way a topology where these point-to-point connections happen. And that's where DWDM comes into play. So what happens in simple Fronthaul topologies is we have a DU that might want to talk to multiple radio units. And when it wants to talk to these multiple radio units, you can use many different technologies. We just heard China Mobile mention passive WDM and mention Xilinx. They mentioned DWDM. So how are these topologies used, right? You might have old networks. You might have lots of fiber. You could take a 25 gig directly from a DU to every single antenna. That is a possibility, but that requires a lot of fiber, and there might not be enough of it. But does that mean it'll never happen? I don't think so. I think there will be topologies where point-to-point Xilinx will happen. There might be passive WDM where you have eFCPRIs going through a tunnel, talking from a DU to antennas. Those are the two orange, brown sort of links that we can see are going through that ring fiber. But ultimately, where density is very, very high, you need to multiplex this data together, because you will run out of wavelengths on a single fiber to talk to DUs to the amount of density that we're looking for 5G. And that is what we call a multiplex group. And that multiplex group will take many different signals, multiplex them together to optimize spectral efficiency going to the antennas. Beyond 5G radio networks, we also have other services that need to be enabled on that unified network, if I may call it as such. So the unified network is going to have 5 gig services. It's going to have residential services. It'll have enterprise services. It might even have multiple service providers. So if you look at certain geographies, you'll see towers are owned and leased by tower leasing companies, and you might have service providers sitting on that same tower. You have to bring 2 different services from 2 different service providers to that co-location. So you might have 2 service providers with their own equipment trying to use a single sparse entity, which is the fiber going to that antenna location. So we can have multiple service providers, we can have enterprise services, we can have access services all sitting on there. How do we get all of those things together? So from this topology, we now need to be able to take the last mile service. And as we talked about the 5G networks a couple of slides ago, which was the multiplex group, the passive WDM, we have to implement within that fiber source, within that network source, the ability to carry access networks, enterprise networks, co-located networks. So right here, what we're trying to show you is you will have co-located services where a DU might actually have eCPRI services going out to a top of a building, but the same network, the same multiplex group might actually be providing access services to enterprises located in that building. So you will have co-located locations very high density in downtown cores, for example, in suburban locations where you might want to bring access nodes. And all of those have to come together in a nice multiplexed group. The 5G last mile will, support additional services, and it'll have to be an on-demand network where things might actually change, right? One of the things might be that some radios shut down at night. When they shut down at night, what happens? Can you actually sell that service, enable new services, monetize that bandwidth for the radios into an access network, for example? People are sitting at home watching TV, or people are going to be on their phones. They might be at night watching TV. That is where you want to bring the bandwidth to. So if you want to multiplex groups, how do you want to multiplex those groups? So we looked at what China Mobile said, and there are many different technologies that exist today to multiplex groups. I've highlighted two of them. OTN is one, FlexE is another one, right? Here a picture just simply shows a FlexE shim. It's not important that you only use a FlexE shim. It could be an OTN based network. It could be a packet based network that multiplexes things. The consideration has to be that multiplexing has to be very low latency. So there are elements in a packet based network that we need to look at when latency is when you're very sensitive to latency. So what would a FlexE shim, what would something like FlexE do to or how will you allow to multiplex with the FlexE shim? So what a FlexE shim does, and that was something that SPN talks a lot about. We wanted to go down and dig one level deep to just show how multiplexing happens. You have many service channels. Those service channels are actually allocated a calendar within a Ethernet link, and that calendar is an extremely TDM repeating calendar that provides a very hard slice of that 100 gig E-link that you can provide to someone at 5 gig increments. So you can take the 5 services that you have, or 5 multiplex locations, put them in that calendar, create a 100 gig E link, and we've just called out some of the elements that our technology enables. For example, we have some hard IP that allows you to do that, and put that into a DWDM ring as a single multiplex group going out. This is what allows the multiplexing of eCPRI signals, access signals, enterprise services into a single group. So how would you implement these DWDM Muxponders, right? So if you look at some of the technology, and we talk about some of that technology earlier, is you have these services, they need to go in somehow, be put together, and be spliced up at the far end, without the far end and the near end knowing that they were ever multiplexed together into a single location. And that is the key. If you start implementing these multiplexing functions inside those elements, it complicates things like radios, it'll complicate your DUs. So you have to implement certain small elements to electrically multiplex the signals together. So again, we use FlexE as an example. It could be OTN, it could be mobile OTN, it could be FlexO. There are many, many different things that the industry talks about. But ultimately, you want to put these things together. The services that come in could be through SFP pluses, it could be SFP 28s, it could be 100 gig services that come in. The line side service, again, doesn't need to be 100 gig. Well, I know FlexE as a standard defined 100 gig PHY, but that's not what it's limited to. As we heard from China Mobile, 50 gig PHYs are very important to them. Maybe 25 gig PHYs become important when you have the right cost point for a optical technology, and that is where optical technology is going to come into play. It is the cost per bit on that optical technology. So we hear a lot about coherent, we hear a lot about DD, but it is going to be the right one that provides the right cost structure for them. So from a adaption point of view, whatever technology we use has to be agnostic to the pipe that we create. Where do FPGAs play into this, right? So ultimately, I'm a Xilinx employee, and I'm talking about our technology here. But what we do is we can create a single element that is a box that can multiplex all of these technologies into what we call an X-Hall system. And it could be packet-based, it could be FlexE-based, it could be OTN-based. Why do all of these, and why not build different boxes? Well, the issues with different boxes are you actually have to leverage and create an ROI business model for every single box, and every single deployment is going to be challenging and different, and every single vendor, every single service provider is going to be different. How many boxes do you actually build? And that is where programmable devices which actually have personalities that can be deployed in an intelligent network come into play. So we are a blank slate. You can actually program us, you can actually build systems in these Fronthaul Muxponders or X-Hall Muxponders in any way, shape or form, put them together and use the right optical technology, and you could be agnostic to the line optics. For example, it could be DMT, it could be coherent, it could be direct detect or gray. That is abstraction that we bring to the play, and we bring the abstraction of what kind of clients that you mix into this. Again, we have a lot going on at the show. If you look, come by our booth. If you look at the OIF booth again, which is a couple doors down that way, there's a lot of stuff going on with FlexE. There's a lot of other stuff with telemetry, 5G Fronthaul stuff going on our booth. You can come please visit us at booth 2807. And I think I've really run out of time here, and I don't want to make my next presenter wait. But if you have any questions, I think we still have a few minutes, so we can talk about some of the demos. Here we do show what is Fronthaul and 50 gig PHYs being used for Fronthaul. But what is really important is another demo we put together. And if you look at this, it's a very high density demo, maybe not applicable to Fronthaul as we talked about, but the applicability is great, because what we've taken and done is we've used colors optics from Inphi as a DWDM direct detect link, which is different from coherent. You can replace that with coherent, and you can actually map a signal into a direct detect link and Muxpond, and actually put clients together into a direct detect link, which have been typically used as point-to-point connections. So there are various different applications and various different ways to be able to use the novel technologies that are aplenty at this show here, in terms of direct detect, in terms of coherent, and how they can be managed and put together to solve application spaces and application requirements for providers like CMCC that we just had a few minutes ago. So this is another really nice demo that we have going. It allows you to use a flexible line system and be able to communicate with routers and ship traffic. Anyway, thank you for your time. Thanks for listening to me. And if you have any questions, I think we still have a couple of minutes.